Now, I have written down some of the formulas and the main graph that we derived towards the end of the last lecture. We were looking at this under-damped response where the damping ratio for a second-order system is less than 1. So this is zeta is less than 1 but larger than 0. Is an underdamped system response. You should be able to derive, if I give you a spring mass damper system, you can derive the transfer function from the input force to the position in the form of the damping, the damper coefficient and then the spring coefficient. You should be able to now comfortably derive this transfer function. And you should be able to relate by comparing this with the standard formula that we introduced last time. You should be able to compare these and derive that the natural frequency omega n is the square root of k over m, and the damping ratio is related to the coefficient m, k, and b together. So I've given you these formulas. It's easy to derive. For the step response, now, today, I would like to work on these details. Now that we know the general big picture, I would like you to be able to work on the details and write out more specifically the parameters, the coefficients, how the x of t will actually look like. So here is where we are. We know the step response is f is a unit step, and in the Laplace domain, it's 1 over s times the transfer function g of s, that will be the output, capital X of s, in the Laplace domain. For a underdamped system response, let's do the partial fraction expansion and write out the general formula. So we know it's going to be containing, first of all, a mode that corresponds to a step. And then second is we would like to work on this. We know it's underdamped. So what we want to write it is s plus zeta omega n square plus omega d square. This is our formula. We want to decompose, we want to write this, not decompose. We want to write the denominator in a way that's easier to recognize from the Laplace transform tables. And then we know that omega d, the damped natural frequency, is the square root of 1 minus zeta square omega n. Okay? This is just writing this slightly differently, and we derived the details last time. In the numerator, we write it in a way as follows. I'm going to use... In the numerator, I'm going to write it this way, where I have s plus zeta omega n factored out, because I want to use the cosine Laplace transform, inverse Laplace transform. And then I have the second term to be related to omega d, written as a scalar times the omega d, because I want to use the sine inverse Laplace transform. Then we would like to define, identify these coefficients. These coefficients, k1, k2, k3, small k1, k2, k3, is to be determined. And one of these is very easy. These can all be obtained through calculus. And one of them is actually very easy. So let's work on this in details. Ky is going to be using similar terminology. We want this to be the same as this. So multiply s to both sides. Multiply s to this and to this. So this s is going to cancel out. And then we're going to leave with k1 plus s times this big chunk of thing. And then I let s to be 0. So k1 is exactly the same formula. S going to 0 times with s times this omega n square, s square plus 2 zeta omega n s plus omega n square. And should equal to this one. I forgot about this one. So this is entire thing under the double line should be the same as this. So it's there's one more s. I will write it in here. So it's s over s. That makes more sense now. So cancels out s in the numerator and denominator, and then you evaluate it together. This is going to be 1 when s is 0. So for these two, k2 and k3, we do a few things. Now we need, so for K2 and K3, we need omega n squared to equal to, now K1 is already 1, so, okay? So I want to decompose it into three things, where this denominator is the same as this, okay? The easiest, the most straightforward way is we need them to be the same. So I'm going to add all of three together on the right-hand side and get s times s squared plus, on the right-hand side, it's going to be s squared plus k2 times s plus this, and then plus k3 omega d. So to make the left-hand side to be the same as the right-hand side, we need everything in the numerator and denominator to be the same. So this whole chunk of terms needs to equal to omega n squared. So that means we have some relationships. This is K2 S times, so S times this term. So the second term is this. And K3 is K3 omega d times S. A small s is missing, a typo. So this needs to be equal to omega n, this whole numerator on the right-hand side. So that means we need, for the s squared coefficient, so let's look at the coefficient. The coefficient for s squared term is going to be 1 plus k2. There's no other term that relates to s squared. So it's 1 plus k2. That's the coefficient for s squared. It has to be equal to, there's no s squared term, so it equals 0. And for the term about s, we have one of them here, and then another one, k2s times omega n zeta, and then another term here. So the coefficient for this one is going to be 2 zeta omega n plus k2 zeta omega n, and then k3 omega d. This has to equal to 0 too, to match the left-hand side. The last term is going to be the coefficient for the constant term. So it's going to be omega n squared plus nothing else. Nothing else is a constant term. So on the right-hand side is omega n squared, and on the left-hand side is actually also omega n squared. So actually this is independent from K2 and K3. Therefore, we know that from the first formula, K2 has to equal to -1, and then K3 has to equal to -1 over omega d, and then these two terms added together. 2 zeta omega n plus k2 zeta omega n, so it's minus zeta omega n. So k3 is therefore going to be negative zeta omega n over omega d. So therefore, we have obtained both k2 and k3 after recognizing that k1 is obvious. So now, with all these, we have capital X of s is big K, is the original coefficient in the transfer function, times 1 over s, and then minus s plus zeta omega n, s plus zeta omega n squared plus omega d squared. And then K3 is negative zeta omega n over omega d, negative zeta omega n omega d. So that's the output, the position in the Laplace domain. The only thing that's a little bit cumbersome, needs more calculation, is the partial fraction expansion, this obtaining of K1, K2, K3. So from here, we can use inverse Laplace transform and obtain, in the time domain, how the signal will look like. So we're going to have capital K, 1 over s corresponds to unit step, and then this term corresponds to a damped oscillation. And the damping is related to zeta omega n, and then the natural frequency, the frequency of the oscillation is determined by omega d. That's the second term. And then the last term is going to be zeta omega n over omega d. It's also decay, exponential decay. So this is the exact output response of the system with respect to a unit step. Any questions so far? Okay, so now, actually things can be even more simplified. So we have two frequencies, the ratio of two frequencies, one natural frequency, one damped natural frequency. And we know actually how they relate to each other. So omega n over omega d, this is actually even more simplified. It's going to be 1 over the square root of 1 minus zeta square. Okay, so we can write it even more simplified. This thing, we can write it as zeta. Okay, so it's zeta over 1 minus zeta square. So we talked about often we want to combine these sine and cosine together as one single sinusoidal function with some phase shift. So you can do that as well. The result is going to be, so let's call this equation star. So now we have this core equation star, governing equation of the response, say explicit. And we can write it as, if we want to combine the two sine and cosine terms together, we can lump them together and write as square root of 1 minus zeta square, zeta. So the overall, I'll write the structure first, cosine omega dt plus phi of t. Okay, so the overall magnitude is going to be the square root of the two magnitudes of the individual sine and cosine functions together. And then exponential decay and phase shift, cosine function with a phase shift. So this one is going to equal to square root of this square plus 1 is actually square root of 1 minus zeta square, 1 over square root of 1 minus zeta square. And here, from calculus, the phase shift is defined by tangent, arctangent of the magnitude here divided by the magnitude here. So it's arctangent zeta 1 over zeta square. This is just a more compact way of writing it using a little bit of more calculus. But it's exactly the same as what we derived line by line on the left-hand side. So from here, now let's look at this graph more carefully and note the few critical points. We have talked about the steady state value. So this is K. This is the steady state value. And then we have talked about the oscillation, the damping of the oscillation is defined by this exponential function. So the time constant tau is 1 over zeta omega n. Let's okay. So roughly plus minus 2% of the steady state value. That's when we reach the 4 times the time constant, and it equals 4 over zeta omega n. The peak time that I ask you to do is defined by the oscillation signal. So the peak time is going to be defined by the period of this sinusoidal function. And if it doesn't have this damping, then this will be one period. From one lower bound, from one lower peak to another lower peak, that's one period of the oscillation. And it's because of damping, then the second peak is shrinking. So this is one period. So it's 2 pi over omega d, and this is pi over omega d. Now we know the time at this specific point. Then we can calculate exactly how much oscillation that I'm going to have. Or in other words, the worst value, maximum value of the output. Okay, so I will call this x max or x peak. Did I use, I will just use x max. And x max, it equals to x evaluated, so this formula evaluated at t equal to pi over omega d. So plug this t value into here, you can get the peak value. There are lots of terms in here, but actually it simplifies a lot. So at this peak value is going to be calculated. If you calculated this one, it's probably easier to calculate from here. So if you use t equal to pi over omega d to here, actually you can see a lot of things going to cancel out. Sine omega d times pi over omega d becomes sine pi. And then cosine omega d evaluated t at pi over t is cosine pi. So those are very easy numbers. So you can actually quickly get this guy. It's going to be k 1 minus e negative zeta omega n pi over omega d times cosine, the cosine term. So it's cosine omega d pi over omega d, or in other words, this is 1. Cosine pi is negative 1. And then the last term is going to be 0 because sine pi is 0. So this one is simplified to k 1 minus e negative zeta pi, and then omega n over omega d, which we saw earlier already. Okay? So that's exactly the maximum value of the response. So the structure actually is very nice. The structure is saying this, right? It is k 1 minus this term. So that means the distance over here, right? This is precisely k e negative zeta pi over 1 square root 1 minus zeta square. Let me write it more clearly with red. I'm going to use red. So it's k, let's see, it's minus sign here and minus sign here, so it's a plus. So it's k plus k times this term. So that means I have already k here. That means this distance is k e negative zeta pi 1 over the square root of 1 minus zeta square. And this is saying I'm overshooting by this amount. So we can know, sometimes we usually call this percentage overshoot concept, like how much is this compared to the steady state value. So how much is this, the ratio between this and this, we call it percentage overshoot. So this is concept of percentage overshoot, or OS, percentage. This is defined by the red term over the steady state value. Okay, so that is simply e of negative, I'm going to write this zeta 1 over square root of 1 minus zeta square times pi. So that is the percentage overshoot. Now, what does this mean? As engineers, we look at mathematics equations beyond just the numbers. The reason why we do this is now you can actually have a tool to, suppose someone give you this graph, someone take a measurement of a system response, okay? He or she doesn't know the actual parameters, but we can do experiments, right? We apply a step to a second order system, and then we have this graph. We can measure the percentage from the graph. We can measure this distance and obtain this ratio. And from the ratio, actually, we can obtain zeta, because this is purely a function of zeta. Everything else is known. Pi is defined. So this actually gives us a way to calculate the damping coefficient for a second order system, right? So take measurements given unknown second order system. You do experiments, you measure it, and then you read from the graph the percentage overshoot. And then using this formula, you can calculate the damping ratio, zeta. So percentage overshoot equals this. So percentage OS equals this. We can calculate how zeta will look like. It's going to be dependent on log. So exponential function relates to logs. More specifically, we're going to have, from here, we have log of percentage overshoot equals to this negative zeta pi square root of 1 minus zeta square. So from here, you can obtain zeta. I'll give you the formula. It's going to be log of percentage overshoot over square root of pi square and log square. This is basically simple calculus. So now in this graph, you can also do many things. Suppose someone give you a graph. You can also measure the peak time. And from the peak time, now you know the percentage overshoot. Now you know, so from here you can read omega d. So you can know the value of this. If you know the damping ratio from that formula, and you know omega d, you can obtain omega n, the natural frequency. So then omega n can be obtained like this. So you can read from graph the damped natural frequency, and you get omega n. So now you know omega n and zeta, and based on the relationship between them and the k, the spring coefficient, the mass, and the damper coefficient b, then you can actually relate a lot about the physical system parameters. Any questions so far?